Victor, first, thank you very much to kindly accept our invitation. It would be really nice if, in fact, if you are here this month, we have like a nice talks in the coffee shop with the people about quantum thermodynamics every day these days. So we have a lot of ideas, and I think we can do something. Maybe you can, after the talk, you can give a time for the people share more ideas, and I'm going to share your email if some students want to get in contact to you.
Sure.
I didn't prepare like your CV presentation, but sorry, like
Doesn't matter.
a bad hoster. But in the co-share, I can send you all the information. Everything is there, like your email, institution, your CV, everything is in the website. So the students they know where you are. Okay. People they're saying they're already online in the co-share. So please, you can start when you want.
Okay. So let me share my screen. Yeah. Can you see my screen?
Yes.
Okay. So thanks, Neto, for the invitation, for arranging everything. It is a pleasure to meet you all and present the works and have discuss about these many-body quantum technologies. So last few years, my group and me and with my collaborators have been working on many-body quantum technologies. So mostly many-body quantum engines. So this the works that I will present now, they are made in collaboration with my collaborators Revati and Uma at IIT Palakkad in South India. Adolfo Del Campo in Luxembourg, Naufal Jassim, my postdoc, and Sai Vinjanampati in Bombay. So the main thing what I want to present is this, say we want to scale up quantum machines, and that is very crucial for the development of quantum technologies if we want to ultimately make, say, industrial applications. But question is how we scale up quantum technologies and if they provide any advantage over single body ones. And finally, say also in the fundamental physics perspective, what are the thermodynamics and universal features in many body quantum machines? So first is I'll talk about these quantum engines with interacting spins. So I'll focus on this quantum critical engines, the universal features in such engines, and then how we can control the performance of quantum critical engines. And next, I'll talk about collective effects in quantum heat engines, and the second part will focus on mostly non-interacting spins. Even though they give some very interesting many body effects. So there are two main, in my opinion, two main kinds of working mediums or systems can make these quantum technologies. So one is this, say, interacting spin systems. So for example, here it is like there are two body interactions plus some local fields. This is a generic model. There can be additional terms also. And they have many body effects such as phase transitions can play important roles. But one very non-trivial thing about this is the Hilbert space dimension is 2 to the power of n in usually. I mean 2 to the power of n. And usually the solutions can be highly non-trivial. On the other hand, there can be another form of mediums in which the systems can be of this form, non-interacting if theta is equal to 1. But if theta is equal to 2, it is two-body interaction, theta is equal to 3 means three-body interaction, and so on. But all the spins are collectively coupled to some external berth. And this coupling can produce very non-trivial many-body effects. And in many cases, it can be shown that these non-trivial correlations can develop between the particles and they will give rise to collective effects, which I will talk about. And for example, in say, if there are many non-interacting particles together, usually the output is n times. It scales linearly with the system size, say, of an engine. But here, because of this collective interaction, it has been shown that the total work output of such engines is super extensive. So that makes very interesting outputs. So I'll talk mainly about these two kinds of engines. Now, first is say this the setup that I will be talking about is is given on the left. Say we have a many body spin chain spin system. Say that take the point D, in which starting from D, which is usually a low energy state close to the ground state, we give an unitary stroke from lambda 2. Lambda 2 is a Hamiltonian parameter. Unitary stroke to A point. It is so it may or may not go through, say, a quantum critical point shown by this red line. Then at A, it is coupled to some thermal bath. And then at constant parameter lambda is equal to lambda 1, it receives heat from the thermal bath and it thermalizes, goes to the point B, which is a high entropy, high energy state. Then we decouple it from the bath and we again give an unitary stroke to come back to the point C. Again, it may go through a critical point. And finally at C, we couple it to a cold bath where it thermalizes with the cold bath. And then this Q in, the heat input minus the heat output is the work output, which can be done to use to do some, say, useful work, say light a bulb or something. So the quantification of the performance is usually given by this work, Q in minus Q out, the power, that is the work divided by the total time period, and the efficiency, that is how much we get out by how much we invest. This work divided by the heat input. So, and all these things, many of them have already been actually realized experimentally as well. For example, in 2016, one of the first works with microscopic engines, heat engines, was done using, say, calcium ion in a ion trap, in which they coupled it to a hot bath, cold bath, and they could run the engine and get out some work and calculate the efficiency and everything. And also later there were many other works, for example, using NV centers in diamond, NV centers in diamond, and other setups where people also showed that, say, if there are some initially coherence in the system, it can lead to quantum advantage. And this, if we talk about quantum critical points experimentally, also they have been realized in many cases. For example, recently in these quantum simulators using cold atoms. So these are all very much experimentally realizable. So first part, I will talk about these quantum machines with interacting spins. Now, again, the setup, I am talking about this kind of an 4-stroke engine. It is an Otto cycle. So as I mentioned, at point D, we start with a very low energy state, which can be, say, for example, at temperature T is equal to 0. So the main question that we want to ask is, if we run the engine, the work output that we get, or work efficiency, power, everything, if they can show some universal scalings. And the reason I'm talking about universal scalings is, if we have a critical point, classical or a quantum critical point, it has been shown for several decades that they can lead to very universal features using scaling relations and RG theory. It has been shown that different systems with very different microscopic properties can have similar scalings with different parameters, say with the distance from the critical point. So the question is, if such a universal property also appears for critical engines, say in the work output or the power. But the problem here is, since this it is a quantum critical, we are considering a quantum critical point which occurs at absolute zero temperature ideally, and any high temperature, any temperature usually destroys such quantum critical properties. So one can expect that such scalings may not hold in this kind of a setup where we also have dissipation. So that is what we want to see, that whether we can somehow get these universal scalings. Now, what is happening is, say if we have this, we go through this D2A here, what is happening is that this universality at first is appearing at A, through Kibble-Zurek mechanism, which I will just show in the next slide. So the excitation energy, the system is getting excited because of this criticality. And the excitation energy shows universal scaling with the rate at which it is quenched. And the nu is a critical exponent, the correlation length exponent, D is the dimension of the system, and Z is a dynamical correlation time exponent. So up to here, it is this scaling is always expected because it is an unitary stroke without any dissipation. But after that, there is a dissipation comes. So the way we model the system is that the hot bath is high temperature, or we consider a very fast quench. Why it will be clear later. So in the next slide. So this is kind of setup we considered, that cold bath is at very low temperature, the hot bath is at high temperature, or otherwise the hot bath is can be at any finite temperature, but in that case we use a very fast quench from B to C. So then now the scalings that we expected coming from this Kibble-Zurek scaling. So just to just remind you of the Kibble-Zurek scaling, what is happening is that there is this adiabatic impulse approximation which says that, say we are driving a system through a critical point, like what is happening here in this case. So so in that case, the system is evolving adiabatically away from a critical point, but non-adiabatic excitations result only close to criticality. This is the adiabatic impulse approximation. What is happening is that here, this is the Xi tau is the inherent time scale of the system. Now the energy gap of the system goes to 0 at the critical point, lambda is equal to lambda c, shown by here. Now there is a inherent time scale of the system which is given by 1 divided by the energy gap of the system. And there is another time scale that is associated with the rate of change of the Hamiltonian, that is given by this delta by delta dot. So there is always this competition between these two time scales. And when this time scale wins, the inherent time scale wins, that is the inherent time scale is very small, that is it takes very low time to relax to the ground state away from the critical point, but close to the critical point this delta goes to 0, so this time scale diverges, so it does not have enough time to relax to the ground state and it gets excited, and this gives the Kibble-Zurek scaling. So what it says is, if we drive a system linearly in time through a critical point, the excitation is given by a generally universal scaling of this rate of quench, where this tau to the power of minus nu d by nu z plus 1. So what we want to see is if this universal scaling also reflects in the work output efficiency power of the engine. Now what we see is that, again going back, so this universal scaling as by the Kibble-Zurek mechanism comes here in the excitation energy, and what we see is that if we do this the work output that is the heat input minus the heat output. Here the plus sign is because of some sign convention. Then the input energy, input heat is given by the input heat in the adiabatic limit when there are no excitations. That is, the system always evolves adiabatically without any excitation, minus the excitation energy. And this excitation energy contains this Kibble-Zedek scaling, universal scaling. And the output energy, that is always equal to the output energy of the output heat of a adiabatic bath. That is because of the way we modeled the bath. If the hot bath is at very high temperatures, or the one of the quenches is very fast, then this thing holds. Now, if then what we see is that one can indeed get a universal scalings of this output work. So then what we can show is that if one of the points, this points A is at the critical point, or the scalings may change depending on whether A is at the critical point or far away from the critical point. So in any case, in both cases, we get universal features. So the work output minus the work output we would have gotten if the engine were adiabatic shows this universal scaling with respect to the rate of the unitary strokes. So the scalings change depending on whether we are quenching till the critical point or across the critical point, but the scalings exist. And those scalings we also got in this power output, which is just one has to divide by by the total time of the cycle, and also in the efficiency we could get some kind of scalings. So what it shows is that even quantum thermodynamics has these universal scalings that are expected in critical systems. And the interesting thing is such universality are usually not expected in finite time few body engines, because criticality exists only in many body systems. So now, as I said, that what it shows is that as we go across a critical point, the work output actually decreases. And this decrease is because of finite tau, which makes it a finite time engine. Now the question is, so how can we control such engines to improve the performance? So that is this next part. So now is controlling quantum engines. So the questions are, if we have an adiabatic engine that is slow dynamics, this enhances the efficiency but leads to engines with zero power. So it is like a classical engine. One can think of it as a classical engine. Say classically we have this container of gas, and there is a piston which is compressing and decompressing, and it is coupled to a hot bath and cold bath. And there, if there is friction in the system, in the piston, then this friction causes loss of energy, and we lose efficiency. That is like non-adiabatic dynamics. And adiabatic dynamics is a frictionless system, in which case the piston does not have any friction, and we get high efficiency in a classical engine. But if there is a friction, we get low efficiency in the classical engine. In the quantum case, it gets transformed to adiabatic and non-adiabatic dynamics. Now, if it is adiabatic, that is slow dynamics, we get high efficiency, but of course, since the time scale is very long, the power, that is the work output divided by the total time, is very small. But on the other hand, if we have non-adiabatic dynamics, that is finite time, then of course it results in finite output power because the time scale is short. But it reduces efficiency of quantum engines because of
yes. Do
yes.
you mind to make a question?
Yes, sure, please.
the work is, we'll find the scaling just for the work, no scaling for efficiency or other.
No, everything is there. Probably, let me check. Everything is, I did not include it. Let me check. Probably it has in the end, it might be. No. So, no, there is also scalings for efficiency. Maybe after the talk, when we discuss, I will show you.
Okay, thank you.
Yeah. Because at least in the power, one can easily see that if power is just divided by the total time. Efficiency is a bit more complicated, but yes, there are also can be scalings. Okay, and so please feel free to stop me and ask me questions.
In the case, the efficiency should decrease, right? Some kind of.
Sorry?
The efficiency should decrease with the disease explains, right?
Yes, efficiency. So, okay, what I mentioned is that if there is adiabatic, then the efficiency is quite high, maximum. But if there is non-adiabatic excitation, then efficiency also decreases, yes.
Yeah, but the decrease depend of the critical, the universality class, the critical explains.
Yes.
Okay.
So, yes, exactly. The efficiency will also decrease because of the criticality. And how much decrease will be there can be understood from these critical exponents. Okay. So, here what we ask is, how can we improve the performance of these finite time many-body engines through quantum control? Now, usually the method used is shortcut to adiabaticity. So for a two-level system, it can be understood like this. Say we have this kind of a Landau's in a transition. So the Hamiltonian is changed as a function of time. These are the energy levels. So what is happening is small energy gas leads to non-adiabatic excitation. So if we start from the ground state, say, and then it will remain in the ground state, but close to the small energy gap, it will get excited. Now, shortcut to adiabaticity method allows the system to follow the instantaneous ground state even for finite rate of driving, that is the red curves. And this is implemented through an additional control Hamiltonian in addition to the original Hamiltonian. And this method has also been experimentally realized. For example, in this paper, they used cold atoms with and an effective two-level system. And this blue curve shows another limit in which we don't care about the instantaneous ground state, but we just want to reach the final ground state. So technically the shortcut to adiabaticity is can be explained like this. So usually what we do is, say we have the Schrödinger equation in which we are given some Hamiltonian H0, we solve for the wave function psi t. Now this psi t can get excited if H0 is changing very fast. Now in shortcut to adiabaticity through counter-diabatic driving, what is happening is we are doing the opposite thing, that is a reverse engineering. So we are given a adiabatic wave function psi adt, which is usually the ground state of the instantaneous Hamiltonian. Now what we ask is, given this adiabatic state, that is the ground state, what is the Hamiltonian required? We should produce this psi ad as the wave function, and this HSTA is H0 plus some additional factors, which goes as lambda dot, that is the rate of change of the Hamiltonian, a lambda, where a lambda is given by this. So it is a very compact, nice form. But the problem comes is, as we see, this a control factor requires knowledge of the full energy spectrum. And this will be problematic for many-body systems. So for these many-body systems, STA Hamiltonians can be difficult to find, and it may not be even experimentally implementable. For example, close to criticality, it has been shown that this STA Hamiltonian can involve infinite body terms. So one possible solution we propose is, say, instead of controlling the system through STO, we control the Bath spectral functions of these engines, which will give rise to something which we name Bath engineered quantum engines. So what we mean is, say we have this many bodies system. Any many body system is a multi-level system. Now, if we go through a critical point, or even if we do not have a critical point, but still it is a finite time engine, but some of the energy levels are very closely spaced, then the non-adiabatic excitations will happen only in these closely spaced levels. The largely spaced levels will not have any significant excitations. So what if we have these hot and cold baths coupled to only the largely spaced large energy gap levels, while the low energy gaps are somehow not coupled with the hot and cold baths? In that case, they are effectively thrown out of the dynamics, and we can expect the performance to be improved. And again, we use this kind of setup, this Otto cycle 4-stroke engine, and again we drive it through a critical point, and we have seen that the driving through the critical point reduces the work output efficiency through universal scaling. So here, what happened? We can show that by the Kibble-Zerek mechanism, energy gaps less than this energy delta hat gets excited with high probability during the unitary strokes. So what we do is, in this A to B and C to D stroke, we consider baths with a spectral function, the lower cutoff at delta hat. That is, for energy gaps less than delta is equal to delta hat, do not exchange energy with the baths. And this can be done experimentally, for example, through some filters, so that only high excitations, high energy excitations are getting transferred between the system and the bath, while the system is kind of it is not kind of interacting with the low energy excitations from the bath. It can be done through some filter, like a harmonic oscillator filter. So the kind of system we are considering are like free fermionic systems, which can be in, say, transverse Ising model, in which case, say, there are different some integrable system in which there can be different momentum modes. So with the different momentum modes, we'll have different energy gaps at the close to the criticality. So so those momentum gaps, those modes with very small gaps will not get coupled to the system, to the baths, while modes with large energy gaps will get coupled. So schematically it is like this. So this is the bath engineered engine, 4-stroke engine, in which we apply the control at the non-unitary strokes, while in contrast the shortcut adiabaticity does the control in the unitary strokes. And this control in the non-unitary strokes is by making these modes kind of fall out of the dynamics. So technically, if we the master equation is of this form, this rho k is the density matrix of this kth mode. These are the Hilbert operators. Rho k, Hilbert operators are in terms of fermionic annihilation creation operators, and these gk are the Bath spectral functions. So these g delta k and g minus delta k, they are considered by this Kubo KMS condition. In any case, the control is this g is considered to be 0 for delta less than delta star, where delta star is the this delta. So all modes with energy gap less than this delta star become decoupled because the g is 0 for those modes. So this is like a Bath engineering. Now we applied this for this transverse Ising model, which is so this model for high HT. So here it has ferromagnetic interaction along the z direction, and a transverse field is applied along this x direction, and this HT is changed for very large paramagnetic field H, we get a paramagnetic phase. But for very small ht, we get this ferromagnetic phase in which all the spins are aligned along z direction. And by Jordan-Newton transformation, it can be mapped to free fermionic to independent momentum modes, like this case. So there we applied this. So this is the plot of the work and the efficiency. So this orange is the adiabatic limit work output, in which case there are no excitations. These red dots is the result in the finite time engine without any control. So as we see, in very large tau, when it is adiabatic, the work output is same as the adiabatic limit. But as we decrease tau, non-adiabatic excitations make the work go down very rapidly. Now, the conventional shortcut to adiabaticity is applied, these blue stars, with four-body interaction. It shows that it is doing good, but again, it also goes down for low tau. Now, this green curve is this bath engineering technique. What it shows is, for a large range of tau, it definitely does better than all the three curves, other curves. So it even goes higher work. We even get higher work than the adiabatic limit using this bath engineering method. And
Victor,
similar, yes.
Sorry, when you use the bath engineer, like for the normal case, ideal case, I understand you have like a gradient of temperature. For the bath engineer, you're going to say you have the same gradient of temperature. Your hot and cold reservoir the same temperature?
Yes, same temperature is same. Temperature is same.
The only thing is difference is the spectral density of your reservoir.
Exactly. Yeah. So, and that difference in spectral density, what it does is it improves the work output and the efficiency significantly, even more than the adiabatic limit. This more than the adiabatic limit was a surprising result. This is never obtained with shortcut to adiabaticity, and this happens because this bath engineering removes some of the modes which do not produce work output even in the adiabatic limit. So
this is not equilibrium, right? For you use the bath engineer, they don't go to the same temperature for the reservoir because the ground state is not seeing the reservoir, right?
Okay, so you mean, okay, when it thermalizes with the bath, it does not really go to the temperature of the bath.
Yes.
Yeah, because some of the energy gaps are not really thermalized. True. Okay. So this finishes the first part of my talk, which is with interacting spins. In case you have any other questions, I'd be happy to answer. If not, I mean, of course, we can also discuss at the
simple question related to the scaling. That one was model independent, right? You just use the general idea of Kibbe Zurich and then you derive that scaling, correct?
Exactly. And then again, we also checked with transversalizing model and it matched, the scalings match exactly. I will show afterwards.
For the Kibbe Zurich, like the kinks, the number of kinks is scaling with the critical exponents too, but the variance in the other moments of the number of kinks is scaled too. So you're going to have like this kind of fluctuations for the work in these kind of models?
Right. I expect there should be also scalings in the fluctuations. We thought about it once. We did not really look at it, but there should be scalings in the fluctuations.
I never saw like people only consider the work and the efficiency, but not the fluctuation of the variance of these quantities during the cycle, right?
No. The next part of my talk also considers fluctuations. Yeah. So, and this universal scaling in fluctuations in this transversalizing or using Kibbe-Zurich scaling have been done. For example, Adolfo Del Campo has some papers on that.
Yeah, in the moments of the
exactly. Yeah.
The king, yes.
Yeah. Okay. So next is the other kind of engine, collective effects in many-body quantum machines. So here I'll be talking about again the Otto cycle, but the main difference I want to specify is, say we can have independent systems in which, say, we have many atoms, these green ones. Each of them are coupled to its own local birth and they are not interacting with each other. So this is like an independent case. But instead here I'll talk about this collective case in which all the spins will be coupled to a bath collectively, so that any excitation from the bath will be shared with all the spins within a kind of like with equal probability, and all the spins will be in a kind of a superposition state. And then even though the spins are not interacting by the Hamiltonian, but because of this collective interaction with the bath, they will have some effective many-body effects, many-body correlations. And they have also been realized experimentally in a optical cavity. So again I will consider this Otto's engine, in which we have this A, B, C, D stroke, and these collective effects, this collective coupling is done in non-unitary strokes here. QH and QC are the heat input, heat output, and again as before, QH minus QC gives the work output. So this in terms of Hamiltonian, this independent coupling is given by we have this total Hamiltonian of all the spins is given by the summation, and each spin has the Hamiltonian like this. So there is this omega is a frequency along the z direction, and each spin is coupled to the bath, to its local bath Br, and there is the bath Hamiltonian. And in case of collective coupling, we have this again the spin part is same, but the interaction with the bath is like this, in which all the spins together is coupled to a common bath. And because of this collective coupling, we can use this angular momentum operators Jz, Jx, where this Jx or Jz are the summation over all the polymatrices. So then what the most non-trivial thing that is happening is, if we couple, whether we are coupling to collective or independent, that leads to very different steady states. For example, in case of independent coupling, each qubit is uncorrelated. So this steady state is a direct product of all the states of all the qubits. As an example, say if the bath is at infinite temperature, then the steady state corresponds to each qubit having this sigma z0, average sigma z0. But if it is collectively coupled, then it causes correlation between the qubits, and then the steady state will be like this in terms of this total this j or j square eigenvalue, and this jz eigenvalue is m, and these are the Gibbs probabilities. Z is the partition function, and in that case, if this t is infinity, then instead of each qubit having this mean magnetization 0, the total mean magnetization will be 0. And similar results we have seen using, we have also used engines with also interacting spins, but all collectively coupled. For example, interactions can be of the form of this jz to the power of theta, where there can be 2 spin, 3 spin interactions, or the LMG model, in which all cases the results I will show in the next slides will hold. But the main thing is, we should be able to construct the system in terms of these angular momentum operators. So what is exciting about this kind of setup is, it is this for independent engines, this specific heat is important because it shows how much heat the system accepts during the non-unitary strokes. It scales with the system size, and the work output therefore also scales with the system size. In case of collective engines close to the Carnot limit, this specific heat scales as n square, and the work output therefore scales also as n square. And this part was shown before by other works by Kudinsky, Nidenzu, in Weizmann, and also later in other works by Petrician group. So what here we saw is that next we consider the fluctuations in such systems, that is the variance. Here in independent engines, the variance goes as root over n, and so the noise to signal to noise ratio, mean divided by the standard deviation, is root over n, which is a textbook statistical mechanics textbook result, which shows that small system size will have large fluctuations, even holds classically. Now, in case of collective engines, what we saw is that the standard deviation instead scales linearly with the system size, and so the signal to noise ratio also scales linearly, and that is we get a quadratic increase in the reliability. This is what we call the reliability, that is the signal to noise ratio. So the reliability increases a lot. With what it means is that if we want to have, ultimately we want to have engines which we can rely on, that which produces some consistent work output efficiency, everything. And for that, if we cannot go to infinite system size, then it is always better to use these collective engines. And we also, these are the plots. So this is the lambda r is the this ratio of these reliability squares, which of course for collective we get n times advantage. So this is the temperature and the total system size. So this this green line is 1, that is in which case we do not get any advantage from collective engines, but any value higher than 1, it shows that there is collective advantage. Then what we see is that for high temperature and high system size, we get a huge collective advantage in terms of reliability. Also, reliability is not the only thing that is important here. Also, say the efficiency, but it has been shown that increasing the reliability can decrease the efficiency. Our efficiency is related to this entropy production. Increasing the entropy production decreases the efficiency. So what is usually happens is increasing reliability will also increase entropy production. So one ratio is quantification is this thermodynamic uncertainty ratio. One always tries to minimize this ratio Q to get a good engine. So and for classical engines, or in many cases, it has been shown that it is bounded by the lower bound of 2. So this is the plot of this TU, or thermodynamic uncertainty ratio. This orange line is for independent engines, which is at 2, and this is also the bound. However, if we use the collective engines, then this is the blue line. So what we see is even the TU is much less than the classical bound or uncorrelated engines. And this is dashed is the lower bound, theoretical bound of this TU. So, and this green dashed is for two-body interacting system with collective interaction engines. So, and this inset shows the TU as a function of again temperature and n system size. Again, as we see that high temperature and high system size gives a collective advantage. So what it shows is that these collective effects can really make highly reliable engines and also very low TU. And this collective advantage actually increases with increasing temperature. So this list takes me to the end of my talk. So to conclude, what I have tried to argue is that many-body systems can offer a rich platform for developing quantum technologies. For example, universal features can be present in many-body quantum critical engines, and scaling theory can be used to see these universal features and also used to control these quantum critical engines. And finally, collective effects can make quantum engines more reliable. And just before I finish, This was for a quantum heat engine, but recently we found that this collective advantage is also present in information engine, like a Szilard engine, but using spins. We could show that these collective effects also occur in those kind of information engines. Okay, so thank you.
I don't think there's only the people for co-share here. I don't know how to ask. They can make questions, but I have few questions if you don't mind.
Yeah, sure, please.
First, like when the collective effects do the bad, that result for n square is for the equilibrium case, right?
Equilibrium means what? You mean that system goes thermalizes with the birth?
Yes.
Like yes.
You're doing the work in infinite time, correct? Because
right, but I should add that this collective effect also reduces the thermalization time n times.
No, yes, this is I expect. But if you look for the transient, like, or the finite time, then how the systems coupled to the reservoir should matter, right?
Right, but there is also one work which I think by the clock group, I think they did this with finite time, and also as far as I remember, they found this collective advantage. I mean, one can always construct a small epsilon shell across around this steady state, so it will reach that epsilon shell in finite time, and then the results I don't think will collective effect will change that collective advantage.
How is this considered? Like this collective coupling came for a weak system coupling, reservoir coupling, right?
Yes. Right.
So it's not, if you consider like a strong coupling between the system and the reservoir, you can get a better scale, maybe?
It is an interesting question. I don't know the answer. I mean, then it will have non-Markovian dynamics, and the dynamics will be much more non-trivial. But I don't know what will happen.
Okay, this is really interesting. Like something we can talk more. And so my collaborators that are visiting here, I don't know if they're just in co-share, they cannot get in the thing. So we have a lot of things probably we want to discuss with you, and I don't know how your time now, because it's just us. So I have just us now here, like that problem for the transistor, okay?
Yeah.
A postdoc is doing now, so probably you're going to have some results soon, okay? So I moved it into the bosonic case first, because you need for the many spins, and even for the case of spin half. I don't know if you know, I checked the reference, but I cannot find. If you change the kind of interaction between the spins, your paper and the previous papers and the others I find in the literature, they only consider the same kind of interaction, right? The sigma z. And the same condition for the degenerate states, everything, right? So my question is, if you consider different kind of couplings, like between the spins, I can find different regimes of quantum transistor, like that's one for the spin half. Another thing is like you only consider the bosonic reservoirs, even the contrary thing. So what happens if you have a bosonic reservoir?
Actually, also one of the reservoirs here was fermionic, like this quantum critical systems. What we considered is, especially for this first part of the talk, the universal scalings, we considered these fermionic reservoirs in which there can be fermionic annihilation and creation operators.
Yeah, in this case, it's only local dissipation, right?
Local in the fermionic space, but when we go to the real space, it is actually highly non-local.
Yeah, but the steady state of this master equation is not the Gibbs state of the Hamiltonian.
No, for this quantum critical engine first part, it was not a Gibbs state. No.
No, if you use, for example, this kind of dress master equation for the eigenstates, probably you should find the Gibbs state.
Yes, usually it is a Gibbs state unless we do something like bath engineering or
Yeah,
we consider for
I mean, if you use the Hamiltonian for the Hamiltonian, the Liouvillean for the eigenvalues, right? You diagonalize the whole Hamilton, then you do the Markov approximations and thing. You're going. That's what my experience. When I use this kind of master equation, I always found a Gibbs state as steady state.
Right. Usually it is a Gibbs state.
Yeah. Yes. But in this case, you didn't consider this general, like this actual thermal reservoir, right? Only this local in this paper.
For these fermionic berths, yes, we consider local, but for the other works that I showed here, they were like these thermal berths, which takes to Gibbs state.
Yeah, relate to this kind of fermionic problem, what we are doing is the that A model with P varying X, Y with transverse field, the one you have the critical phase in the middle of the phase diagram. So that thing is interesting because the spectrum there is fractal, right? You have like the localized, the normal A model, you only have two phases. Only the critical point is fractal. If you have like this pairing term or transverse field in the spin model, you're going to broken the symmetry, so you're going to have like a big region or it's critical. And this critical region, the whole spectrum is in the vectors has some fractal structure.
Okay, I don't know about the fractal, but I mean, I'm not familiar with the fractal structure of this transversalizing model, but yeah, I mean, okay, it is probably.
Yeah, so that's a thing, like, because usually for this term machine, the spectrum is the most important thing, correct?
Yes.
If the harmonic is boring, nothing going to happen. Doesn't matter which the system you have. So you have a harmonic spectrum, you're going to get every time the same result, right? Like any levels with all harmonics, the same gap, nothing's going to happen there. So that's one problem we are start to do now, students. And then if you have interest, it would be nice to discuss with you when you have some results. Because when you show now the Cube Zurich, because I did the Cube Zurich in that model. I can show we have all the scaling, so you can check if we're going to see the same thing in the O2. Because it was like, the student was just like this fractal the spectrum could be something interesting. Let's check how will be this machine, the engine. But now after you talk, like there's a lot of things you can verify. I remember that like I was only trying to verify the power over the efficient scale for the Fazio paper.
Related to that.
But this is not, for example, this scale is not related because you use this local Liouvillean.
No, even if we also use thermal berth, just the text it to a Gibbs state, even then it works.
Okay.
I mean, with the local thing is in some cases, this kind of local berths, one can use this actually analytically do many stuff. But in some limits, these local berths actually it can be shown that goes to a usual Gibbs thermal berth. Even in that case, the scaling solved.
Interesting. And another problem that the students here, you're studying the, I don't know if you're familiar with this Habib-Stark, an isotropic Habib-Stark model. You have the normal Habib model and isotropic because the control rotate term is different. So you have G1, G2, and then you have plus I-Stark term on sigma Z A dagger. Okay. And this model has first order and second order phase transition. So there's just how the looks super simple, right? You have like just two-level system coupled to a mode, and then you're trying to see if you can see this kind of criticality in the engine in this model. But we have like I have some numerical problems now because the second order phase transition is kind of different because everything diverges. So the number of photons diverge. So to do numerics is every time you increase the truncation, change the result. So I don't know how to handle this yet. So probably going to just get close to the critical point, but not at the critical point to have something, you'll be right. And then after the critical point, they have this spectrum collapse. So all this the spectrum is degenerate. Everybody going to the same number. So there's no much. It cannot do a engine with this kind of part, right? If the spectrum is full,
I mean,
two states. Yes, I think you can check it, but this spectrum is really strange. I have no idea if it's like stable physics makes sense. That's how it's found. But it's really interesting because one thing we're seeing, whereas you have the first word phase transition and just the quasi crossing, when they just is not phase transition, but they get close. There's no difference for the efficient, at least. So a real crossing or just almost like a quasi-degenerate state for the efficient doesn't matter. You're going to see the same thing.
Okay.
So look like the first word phase transition is not really important. Like the get close is important, but if they close or not doesn't matter. So this is I think the interesting result. What else? Yeah, so if you're interested in this kind of problem, can you have like some results? I can send you can talk again, because I feel
sure. I mean, I don't know. I cannot remember any work on this quantum engines with first order phase transition. That would be quite. I mean, even if the criticality does not change anything, even that would be, I think, an important result. Yeah.
No, at least you can. For example, for the model for the Stark Hobby, look like a lot as the Dick results, but you have just one atom there, and the critical exponents are different for one phase transition and another. But the first part, like where you can see the normal phase, is almost the same. It doesn't matter the anisotropy in the system. So the anisotropy then this normal phase, but after this, the anisotropy can increase the efficiency. You can get like where the Hubble model there is nothing, you don't see anything, and the anisotropy in the system can show like increase the efficiency. Now, because the system is small, that paper of the Dick, we didn't need like the power because it was hard. Was to make the time evolution of the system and all these things. But in this case, we're going to do the power and this kind of look for this scale. It'll be interesting. If you're interested, I can send you the reference for the A model I'm working. I just I feel I was just thinking today, like we can probably get some analytical results there. And so I'm going to think better, because the students are just doing the numerical thing. So it's an interesting thing because it's
I think yes. I mean,
no any reference of quasi-periodic system as working fluid for working medium.
No, there are references on this quasi-periodic system like this Aubrey-Andre Harper model or AH model. In which not an engine but a quench to the quasi-periodic system to see this Kibble-Streck scaling or what happens.
Yeah, no, this is what that's the paper I did. You could observe.
Okay.
Well, my first contact with this model.
No,
I saw. I did like a search. I just found one paper just looking how the current, like I have this system, two different reservoir, how is the thermal current of the system.
There is some paper, I think, by this Patrick Potts or some group from Ireland, I think, in which they have these two reservoirs at the two ends using this AH model.
Yes,
They did,
Yeah, but even there, they use a kind of phenomenological thing to treat the currents. There's no master equation, nothing like it. They're saying, oh, it should be Fourier, the temperature. So it's kind of phenomenological treatment. So I have no, I ensure like that for the closed system, for just the Hamiltonian, you can go for 1,000 spins easily. So you can see some criticality there, right? But if you, and so what they're doing first will be the ideal case, right? So you don't need master equation. So you're going to thermalize, build the gives, do all the calculations, and see if there's anything interesting in this critical phase. That's the whole idea. For the extended and localized phase, there's few works that people already did. Like many bar localization as engine, they did some work like that. Only have two phase, but I hope this critical part of the spectrum it gives them something new for the thing. And this model they have like they had a second order phase transition in one direction, but normal like I'm not a second order phase transition at another point, like kind of close over. And we did some studies in the dynamic phase transition. This model, I don't know if you can relate anything a dynamic phase transition with some engine thing. I don't think there's nothing, right?
No, I don't think so. No.
Yeah, this could be interesting if you do the finite time and see what happens with when you have the zeros of the Low-Schmidt echo when you go from one phase to another.
I mean, I also thought about this dynamical phase transition engine. I think, so this modeling of it would be, but that would be interesting. I don't think there are any works on that.
I hope to get some, at least the ideal case for the work to see. This is what I'm going to get and see if we can do some analytical result, and then I will message you. I may.
Sure. It
sounds
interesting.
For the transistor, now how I told you, I was kind of no time to code any things, and now this postdoc is good, so I hope we're going to have few results for different things. So there's this spin half with different couplings, different kind of reservoirs. He's going to put negative temperature in the control. There's a lot of ideas that passed to him. He knows how to do all these things. So it's just how I say this. It's not a complicated system, but you need machine time to compute the derivative there, right? I think it's the only thing. Yeah, you need to run a lot. After you do the code, you just need to let there and see what happens to get that logs. But the idea is quite simple. So, So Victor, thank you very much for your time. I mean, for me, it was really good. Like I read your review, but now when you were talking about, okay, that's one thing you were saying. And I didn't. It was my bad. The physical review research I got but I just this is the physical review research. I didn't read like how I should. So I'm going to do this homework tomorrow. And if I have any problem, I'm going to message. Okay?
Yeah, sure. And again, thanks again for the invitation. Bye.
So bye bye. Have a nice day.
You too. So we'll keep in touch and discuss more about the transistor.
Bye bye.
Bye.